These are the answers to the questions in the 2.8 Energetics Fact File. Question 1. Many enthalpy changes, including enthalpies of combustion, can be determined by experiment. Others can be deduced using Hess's law. State Hess's law. So, quite simply, you're going to say that the enthalpy change for a reaction is independent of the route taken and we also have to give a proviso, so providing or provided the initial and final conditions are the same. So 2 marks for that, 1 for each part there, either side of the comma. So then define the term standard enthalpy of combustion. So we're going to say this is the enthalpy change when 1 mole of a substance is completely burnt. In oxygen, and you always have to add in these enthalpy definitions under standard conditions. So next we have to use the standard enthalpies of, that should say formation. There are a few typos in these, and they can throw you off if you're not sure what they are. So use the standard enthalpies of formation given in the table below to calculate the enthalpy change for the complete combustion of methane. What I'm going to do is draw my little cycle out down below here. So CH4 plus 2O2 giving CO2 and 2H2O. So enthalpies of formation, that means we've got the elements. Now I don't need to write out what they are. I can just write elements, it doesn't matter because we're looking at the top equation being balanced. That's the most important thing. So what I'm going to do then is to put my arrows on for the information that we've got. So the enthalpy of formation of the methane is minus 75, carbon dioxide is minus 394, and the water is minus 286, and we've got 2 moles of it, so that's 2 times minus 286. I'm going to do that up here, so that would be, bear with me, 286 and 286. That's minus 572. So I like to draw my arrow on like this, and then my total becomes minus 75, and then I'm going in the opposite direction, or sorry, it's plus 75 because I'm going in the opposite direction here. So I'll have to change the sign, and then it's minus 394 minus 286, which gives us a total of minus 891 kilojoules per mole. The other way you could do that question is to say that delta H is the sum of the formation of the products, take away the sum of the formation of the reactants, and then so that would give you, using the values in the table, minus 394 minus 2 times 286 minus 75, which is the same thing. It still gives you minus 891. So some people like to do it the second way with the summation. I prefer to do it the first way with the little cycle. So in B, the enthalpy changes can also be calculated using average bond enthalpies. When bond enthalpies were used to estimate the enthalpy of reaction for the combustion of methane, it was found to have a value of minus 698. So complete the enthalpy level diagram for this reaction. We're just looking for the two levels here drawn on, so reactants and products, and then a little pathway drawn like that. What is meant by the term average bond enthalpy? Well, it's the energy required to break 1 mole of a given bond and then you have to say this next bit's very important, averaged over many compounds. Okay, part 3. Using the estimated enthalpy of reaction and the bond enthalpies given in the table below, calculate the bond enthalpy of the carbon to hydrogen bond in methane. So if we write the equation down here again, it was in the last page if you remember. So this equation, CH4 plus 2O2 gives us CO2 and 2H2O. And if we look at the bonds being broken, first of all, we have we're looking at the bonds which are being broken here, which we know which are 2 of these, so 2 times 4, 9, 6. And on the right hand side then, the bonds which are forming, we have 2 of the carbon to oxygen in carbon dioxide, so 2 times 7, 4, 3. And in water we have 2 bonds in each molecule. So that means we have 4 of these, so 4 times 4, 6, 3. So the total for the bonds broken is going to be this 496 times 2, which is 992, plus these bonds in the carbon to hydrogen, or in the methane. So methane's like this. So there are 4 carbon to hydrogen bonds in here. So that plus the 992 is the total on the left. The total on the right then is, when you add these together, you get 3,338. So a little bit of maths, 3,338, take away 992 is going to give us 4 times this carbon to hydrogen. So that gives us the carbon to hydrogen bond, when we work it out, is 1,648, sorry, for 4 of them. So we divide that by 4, 1648 divided by 4 is 412 kilojoules per mole. Okay, number 2, point 0.47 grams of hydrocarbon was completely burnt in air. The heat produced raised the temperature of 200 grams of water by 28.2 degrees C. Standard enthalpy of combustion of the hydrocarbon is 2,220 kilojoules per mole. Specific heat capacity for water is 4.2. Which one of the following is the molar mass of the hydrocarbon? So we're going to start by doing Q equals mc delta T. And we sub in the values. We've got 200 times 4.2 times 28.2. And that gives us 23,688 joules. So then we want to know the number of moles of the hydrocarbon. So that is the number we just worked out, the 23,688, divided then by this number. It's given here in kilojoules, so we have to convert that to joules. So that becomes 222,000. So that means we have 0.01607 moles. And then we can work out the molar mass. The formula mass is the mass divided by the moles. So that means then we have 0.47, which was at the very start of the question, here, divided by 0.01607, which gives us 44 as the formula mass, and that is answer B. That's a lot of work for 1 mark. Number 3, some ice packs used to treat sports injuries contain ammonium nitrate and water. A capsule containing the water is broken, and the ammonium nitrate dissolves and the temperature falls. So the following results were obtained when ammonium nitrate was added to some water. The mass of the water is 100 degrees, the ammonium nitrate 5 grams, the initial temperature 25, and the final temperature 24. Specific heat capacity is 4.2. So before I do anything else, I immediately would see there that we're going to need to work out the temperature change, delta T, and it's going up by 0.9 degrees. So calculate the enthalpy change. So Q equals mc delta T. So M is 100 because it's the mass of the water. Don't be seduced into using the 5 grams of the ammonia. C is 4.2 and delta T is 0.9, and that gives us 378 joules. So then how many moles of ammonium nitrate were used? So the moles is the mass over the formula mass. So we have 5 from the question here, divided by 80, which is the formula mass of the ammonium nitrate, so that's 0.0625 moles. So then calculate the molar enthalpy change for dissolving ammonium nitrate in 100 grams of water. So we have 378 from our first part of the question, and then the number of moles we worked out was 0.0625. So divide through by that and we get 6,048, and that's joules per mole. So then it says one manufacturer makes an ice pack containing 120 grams of water. What mass of ammonium nitrate would be needed to produce a temperature fall of 25 degrees? So we can do that this way. Q equals mc delta T, which is 120 times 4.2 times 25, which gives us 12,600 joules. So then we know that it's 6,048 joules per mole, so 6048 times the moles, would be 12,600. So the number of moles then would be the 12,600 divided by 6048, which is 2.083 moles. And then the mass is the number of moles times the formula mass, which in this case is 80, which gives us 166.67